So the basic question on Quideo 4 starts out by explaining a scenario where a census bureau is trying to find the percentage that the average household spends out of their total spending on housing. Um, and they find that percentage to be 31%, but a home builders association is going to challenge that and say that in their area they believe it's actually lower than what the Census Bureau reported, which is 31%. Um, so we are given a null hypothesis and then the alternative hypothesis, which was the hypothesis that the Home Builders Association proposed. So, what is believed to be true by the Census Bureau, the null hypothesis, is that on average, people are spending 31% of their total spendings on housing, and the alternative is just that the mean is actually less than that. So we're given the standard deviation and the mean. So question A then asks, what is the sampling distribution of the mean percent that the sample spends on housing if the null hypothesis is true? And then we are to sketch the density curve. So this basically what the sampling distribution is just the density curve. So the first thing I started out doing was making sure that we could indeed assume this graph to be normal. So I tested that by first of all seeing if the sample was big enough, which it was. NP was greater than 10, QP was greater than 10, and there are more than 400 adults in the US because you would multiply 40 by 10. And so we can indeed assume normality. That the problem doesn't actually state that the sample of the 40 households in Cleveland was random, but we're just going to assume that it was. And so in order to sketch the sampling distribution, well, first you need to know what the mean is, which is 31%. We are assuming because we start out assuming the null hypothesis to be correct. And then to find our standard deviation, we take the standard deviation of the population and we're dividing it by root 40. And you get about 1.52, which you would expect it's going to be less. It's going to deviate less because we're taking a mean here. So the mean of 40 people versus just everyone, it's going to be a smaller variation. So once you do that, you just put the mean right in the middle, and then I did 3 standard deviations out, so you merely add the standard deviation on each side 3 times, and that is what the sampling distribution looks like. We're now asked to suppose that the study finds 30.2% as the mean, so mark this on the axis. And then suppose that the study result is 27.6%, and then also mark this. And then we're asked to explain why one result is good evidence that it actually is less than 31%, whereas the other one is not. So if we see 30.2% is right there, so it's not quite even a standard deviation away. So you really can't say that that's too significant of a significantly far enough from the mean to completely just reject the null hypothesis, because as you can see there's still a lot of data before that point. So if you were to look at the area, your p-value is going to be it's going to be still fairly moderately high. So there's a large amount of samples that appear below 30.2%, even when we're assuming the null hypothesis to be true. However, when we're looking at the number of samples that would be expected to be below 27.6, that is actually a lot fewer. You can see that I marked that point on the graph right there. And and there's not many samples, the p-value would be small. So in other words, there's a low probability that you would get a mean that small if the null hypothesis was true. So that's why this provides a little bit more solid evidence that maybe it's actually not true, because it's pretty improbable you would get a sample with that small of a mean if it was true. So then looking at part C, it's just asking us to shade the area under the curve that gives the p-value. So your p-value is just the area under the curve up to that point pretty much. So the probability that that could happen, anything lower than that. So it says, note that we are looking for evidence that spending is less than the null hypothesis states. So looking right here, I shaded the area from negative infinity, basically, because it never really touches the x-axis, to 30.2. And so you'd expect a really small, not a small, you'd expect a moderately sized p-value, because again, it's not quite even a standard deviation away. So we can pretty much just do that just by shading, and that gives all the evidence that we need, like I explained in part B. The advanced question gives us a Pew Research poll looking for the proportion of teens who have lied about their age online to gain access to websites. They polled 799 U.S. teens. So Part A wants us to find the margin of error for this poll with a 95% confidence interval. So that's pretty simple. You just use your margin of error equation, which is based on your confidence interval as well as your sample size and the proportions. So, and it is a plus or minus situation, because it is that much above or below whatever the mean was measured to be or observed to be. So if you plug in 1.96 for your z, which is the z value when creating a 95% confidence interval, and you plug in 0.49 as your probability of success, q as 0.51, your probability of failure, and then noting your sample size is 799, you get about 0.0347 above or below the measured proportion of 0.49. So part B says explain in context what this means. So a margin of error for a 95% level of confidence means that we're 95% confident that the true proportion of teenagers who misrepresented their age is within 0.0347, the margin of error, above or below the reported average, or proportion, better yet, of 0.49. So in other words, we're 95% confident that the true proportion of teens who misrepresented their age is between 0.4553 and 0.5247, which I got just by adding and subtracting that margin of error from the original proportion. So now if we only need to be 90% confident, it asks, will the margin of error be larger or smaller? So just looking at it purely mathematically, we know that it's going to be smaller, because the margin of error is given by the equation shown right there. And if you only need to be 90% confident, your z value is going to go down. So therefore your overall margin of error is going to go down if that's the only thing that's changing. Which also makes sense conceptually, because if you don't need to be as confident, you can have a little more leeway and therefore have a smaller margin of error. You can be more sure that that what you are sure about is a smaller amount, if that makes sense. Now, for the AP question, it tells us that a random sample of 1,026 U.S. adults was asked a question. Basically, they want to know, would you like Congress and the President to change the Social Security system? And so then it gives us the proportion of people who said different responses, whether it be overhaul the system or just leave it the same. And so we're asked to create a 95% confidence interval for the proportion of adults who would respond, make major changes to the question. And then we're also asked to interpret this. So the best thing to do when you're asked to calculate and interpret is to do PANTS. So start out identifying the parameter of interest. We're just going to say X is going to represent the proportion of adults who would respond, make some major changes to the question. We want to check our assumptions as well. NP is 1,026 times 0.39, which is about 400, obviously greater than 10. And QP is around 626, also greater than 10, so we know it is large enough. There are more than 10,260 adults in the U.S., so we're pretty sure that it's small enough. We're not going to have to worry about the samples not being independent or anything like that. And the problem also told us that the sample was randomly selected, so we can check off all of our assumptions there. Then we're going to name the test. So we have one proportion, and we're supposed to be making. So our test we're using is a Z interval test, because we have one proportion and we're trying to find an interval. So we can use the equation for margin of error, so we know our mean, and the margin of error here would be Z times root PQ over N, because it's a proportion, and we know all those things. Since it's a 95% confidence interval, our Z value is 1.96 again, and so when you add and subtract that to 0.39, which if you look was the proportion given to us in the problem, we get this confidence interval 0.3601 to 0.4198. So what does this mean? So we have to interpret that. This means that we're 95% confident that the true proportion of U.S. adults who would respond, make some changes, is between 0.3601 and 0.4198. So that's what the confidence interval means. And so what the confidence level means, 95%, that means that if we construct a bunch of confidence intervals, 95% of them will contain the true proportion of U.S. adults using this method. That's basically what it means. Will contain the true proportion. So then part B is explaining that an advocate for leaving the system commented that only 39% of adults responded they want only major changes, and then 41% responded they want minor or no changes, so we should change it. And then why is this misleading? Well, it's pretty obvious to see that it's misleading because it completely misses out on the 19% who want to completely overhaul the system, which when you combine that with the 39%, you get 58%, which compared to 41% shows that a lot more people want to change the system. So they completely excluded that and just used the minor adjustments and leave the system and compared it to just the major changes instead of overhauling as well. So that was kind of an attempt to mislead you into thinking, well, more people don't want to change things.